Hi everyone, I'm Wenkai from Aarhus University in Denmark. I'm excited to present my paper with Hans-Jörg in TRX Viz 2020 on trust in VA. To talk about trust in VA, we need to go back to the origin of VA, where it was intended to bring the unique but different abilities of human and computers together. Computers are good at indexing and searching a large amount of data as well as computation, while humans can use their knowledge and creativity to generate insights and solve problems. VA depends on the close cooperation between human and machine to work together through different inputs and outputs. And when we talk about the close cooperation, the concept of trust becomes increasingly important. So first, let's define what is trust. Researchers might have different definitions on trust, but one widely accepted definition of trust is the belief that the trustee will act in the best interest of the trustor in a given situation. In the context of VA, the primary goal or the best interest of users is to identify and visually distill the most valuable and relevant information content. We therefore define trust in VA as the trustor's belief that the trustee will help them correctly identify and visually distill the most valuable and relevant information content. There have been some previous research on trust in VA. However, many of them have talked about trust in a dichotomous way of trust and distrust, focusing mostly on building users' trust in VA system and avoiding distrust. However, there are a couple of issues with such approach. First, we often do not and should not easily fall into the extreme side of trust or distrust, but usually retain some degree of healthy skepticism while working with someone or something. It is therefore important to identify such intermediate states such as untrust, which denotes the state where users have not developed full confidence in the VA system. Also undistrust, which emphasizes the state where users become suspicious of the VA system but have yet fully distrusted it. Another perspective missing here is how trust and trustworthiness are two related but very different concepts. Trust, as we discussed before, is a belief that the user might have on the system. However, when a user fully trusts in a system, the actual trustworthiness of the system might not be on the same level. This is problematic, as users might misuse the system because of such mistrust. For example, they might interpret results with very high uncertainties as trustworthy. Such blind trust will lead users to make questionable decisions based on the information they got from the VA systems, which might cause even more trust issues when they later realize such trust was not justified. On the other side of the spectrum, misdistrust denotes situations where users put distrust in a system that are actually trustworthy. This is also problematic, as once users cross the limit of forgivability, they might disuse and abandon the system, therefore making it nearly impossible for the system to later redeem itself. In this paper, we therefore emphasize that in addition to trust building, which can help to avoid the abandonment of the system, trust calibration is equally important to avoid unmet expectation from users, misuse of the VA systems, and later regrets that such misuse might cause. Here, we define trust calibration as aligning the trust that users put into a VA system with the system's actual trustworthiness through various means, such as communicating uncertainties, providing visual cues, and previews of the end results that user can expect from the system, and indicating analysis paths that have shown to work for similar data in the past. To dissect trust calibration in VA, here we present how users might often have some unmet expectations in each element of the VA pipeline, as well as their potential solutions. First, the VA pipeline starts with the input of data. As much as we try to collect raw data and think that they are objective and truthfully reflecting reality, data are often subjectively collected through certain technical and social lenses. National population census data in some countries are collected through investigators going into every household and might be subject to various human errors. Natural sciences researchers place sensors with varying accuracy in locations that they deem as reasonable to gather data for their research. Tech companies collect user data through their own algorithms, selecting data that are relevant to their fields of business, easy to access, and legal to be collected. As such, Even the data in the most original forms are conceived before collection process and limited by various technical and social constraints. It is therefore important to bridge this gap by communicating all the metadata to the users. Uncertainty visualization is a frequently mentioned approach to communicate quantitative uncertainties, while for qualitative uncertainties originating from the process of data gathering and preprocessing, communicating the data provenance is an established approach. Subsequently, data go through the computational process to generate results that fit into the visualization rendering. Ideally, users are expected to be able to understand and interact with the underlying computational process, and the algorithms are expected to be fair and unbiased. However, most computational software are used as a black box that runs in isolation, providing no output other than the final results when it is ready, and defeating the purpose of using a visual interactive data analysis. When errors arise, users rarely have the option to probe into the computational processes to inspect the potential causes, therefore being unable to verify what went wrong and calibrate their trust level accordingly. Moreover, many algorithms that support the computational process can be biased due to limited training data or specific purpose of it. Results from such algorithms might lead users to mistrust the system if the results are consistent with user expectations. To counter such issues, user involvement in the computational process has been proposed as a solution, which in turn provide knowledge about the algorithms, insights into how they run, as well as agency to users to calibrate their trust levels. To cope with algorithm bias, tools such as FairVis has been developed to uncover potential biases in the algorithms. Next, the computational results run through visual rendering as a means for human users to gain insights. However, most VA systems provide a limited selection of visual mapping and rendering techniques that might not communicate the underlying data accurately and provide effective means to discover insights. Issues such as overplotting and smoothing can also lead to important information hidden at sub-pixel resolution, therefore hindering users from gaining insights. For such issues, some form of visualization design guidance and linting can help to avoid design mirages that fails to communicate the underlying results properly, while communications about the rendering constraints can notify users to take actions such as zooming in certain areas to discover insights that might have been hidden. For interactions, when users take actions in a VA system, they have conscious or subconscious expectations of the user's reaction regarding logic, time, and space. Discrepancies between these expectations and the provided reaction pose a threat to VA system's trustworthiness. For example, in coordinated multiple views, users' action in one view are expected to influence several others. Yet, if this influence is not clearly represented across the different view spaces, or the action takes too much time to propagate through other views, users might not be able to understand which of their actions impacted in which ways the other views and misinterpret the underlying logic, leading to misdistrust. A way to counter such trust miscalibration is to communicate the system response and latency regarding users' possible interactions. For example, previewing the system reaction and time, as well as displaying visual connection between visual elements that respond to each other. On the other side of VA system is human users, and variation in their perception, knowledge, judgment, and situational state can also make the users not trustworthy and have an important influence on trust calibration. Users expect them to be able to accurately perceive information from VA systems. However, people might have different perceptual abilities, such as color blindness or lower color sensitivity with growing age, and can be subject to perceptual errors such as change blindness, as well as line width and sign illusions, regardless of individual predisposition, both of which will hinder trustful visual communications between the VA systems and users. There have been attempts to address such perceptual issues. For example, tools like CALIBRATION and dissect can help to adapt to different color blindness. Common angle plots were proposed to address line width illusions. Running analysis with the VA system, users internalize the resulting information they yield from the system through their existing construct of knowledge. Users are expected to have enough and accurate knowledge to extract insights. However, domain knowledge might make users overconfident and limited by their own knowledge framing, and insufficient domain knowledge or knowledge about the VA system might make it hard for users to judge the plausibility of the results and unable to leverage the VA system to generate truthful insights. To solve such issues, Providing interactive means for branching analysis and what-if scenarios can help to provide alternative analytical paths. In addition, knowledge-assisted visualizations have been proposed to capture and reuse the knowledge users and potentially other users generated from previous sessions to help them better utilize VA systems to generate insights. Furthermore, human judgment underlies the more subjective cognitive processing of information. An ideal VA user should have objective and comprehensive understandings of all relevant information. However, cognitive biases and different personal factors might lead one to deviate from rational thinking. For example, we tend to seek meaning in things and interpret things with our own experiences, often seeing patterns where there are none, or only seeking for information that confirm our previous preconceptions. Seeing a lot of confirming evidence in a VA system can lead to mistrusting it. This is a clear miscalibration, as the system always shows the full story, but the user only pays attention to one side of it. Personal factors such as culture, gender, and personality can influence how one makes decisions too. For example, cultures with high uncertainty avoidance tend to make unnecessary conservative evaluations, while cultures with low uncertainty avoidance are more prone to take risky actions. To counter cognitive biases, some debasing approaches have been proposed in VA, such as different forms of guidance and analytic provenance. In addition, personalized visualizations can take into account personal factors and adapt to different users. Last but not least, users expect that their decisions are stable and not subject to their mental and physical environment. However, this is not true either. Users' mental state and physical environment have been proven to have great influence on their behavior patterns. Mood has been an important element in decision-making. For example, negative moods are associated with introducing changes rather than maintaining the status quo. This also impacts the use of VA systems. For example, using VA system with a negative mood might make users more likely to introduce unnecessary changes. Regarding physical environment, although VA tasks are usually performed in a consistent indoor environment, it is not necessarily optimal. Especially social factors such as shared offices, interruptions, and distractions can make a focused, in-depth analysis session almost impossible. This leads in turn to an increase in perceptual errors and an inattentiveness to one's own biases and algorithm biases alike. Tracking physical parameters like eye gaze and EEG has been proven useful in gauging user internal situational factors like mood and intentions. VA system can also ask questions about user intentions and external situations before they enter the analysis process. Such information can be used to adapt the VA system to situational factors. After dissecting trust calibration in all the 8 elements of the VA pipeline on both the system and human user side, we conclude our paper as following. In this paper, we make a clear distinction between trust building and trust calibration, and bring attention to the trust calibration for matching users' perceived trust and the actual trustworthiness of VA systems. However, much more research needs to be done to gain a more comprehensive understanding of trust calibration in VA. To begin with, trust building and calibration can stand in conflict with each other when actual trustworthiness of a VA system is low, and thus building perceived trust would actively miscalibrate it. Therefore, it is important to consider and investigate how trust building and calibration should coexist. For example, when a user mistrusts a system, it is important to disclose the untrustworthy part of the VA system to calibrate trust. However, one can easily go overboard with such calibration and can lead users to distrust and abandon the system. Furthermore, although there have been some research on evaluating trust levels, tracking trust calibration can be a dynamic process that requires continuous monitoring of trust and trustworthiness. How to evaluate trust calibration is therefore an important but complicated question to address. Potential ways can be through surveys as well as tracking user actions and physical measurement. But is there any new way to do this? For example, providing some questionable information from time to time to detect if users are still alert and aware of potential issues in the VA systems. In addition, as new VA approaches emerge, trust calibration can become more intricate. Progressive VA brings up additional trust issues when working with incomplete results. Mixed initiative VA starts to ask about the trustworthiness of users. And collaborative VA introduces interpersonal trust to the VA process. Both theoretical and empirical research is needed to fully dissect and investigate the trust dynamics in corresponding VA approaches. At last, we hope this paper provokes new discussions and considerations on such research questions, and thank you for your attention.